My name is Daniella Tola, and I will be presenting the paper, A Cosimulation-Based Approach for Developing Safety-Critical Systems. This paper is part of the outcome from my master thesis that was created at Aarhus University. The agenda is briefly giving a background information for the motivation and the case study, introducing the methodology used and the development process of using this methodology with the case study, followed by a demo of running a cosimulation using the InterCPS toolchain. In the end, I will give a brief discussion and conclusion on the project. So first I will introduce the two main definitions, a safety critical system and a safety case. A safety critical system is defined as a system that if an error occurs or it malfunctions, that it may damage its surroundings or its environment. So it could potentially, if it fails, it could potentially kill a human or injure a human being or an animal. So in order to ensure the safety of these systems, a safety case usually must be created. And a safety case is a number of documents that provide sufficient evidence that this system is adequately safe to deploy. And the safety case will usually be presented to a regulatory body that will need to determine if this safety case actually demonstrates that this system is safe to deploy. So the motivation in general for using cosimulation when developing safety critical systems is that systems in general are becoming more and more complex. More software is being put into systems. Everything needs to be autonomous, everything needs to be smart now these days. And that's good, but if these systems are safety critical, then it means you will need to spend much more time on determining how safe this system is actually, and much more money on ensuring the safety of this system. So this is really time consuming. When there are different ways of developing safety cases, and one of them is developing the system first and then developing the safety case. The problem with this is that you can end up with needing to do large system redesigns. For example, if you have a machine that should slice something, and let's say that it was designed so that the operator just has to press one button, hold one button down for the knife to slice. The problem with this is that it can be unsafe if the operator uses their left hand, uses their other hand, puts their other hand under the knife without thinking about if they're tired or something. I mean, this is part of being human, that we can make mistakes. And then presses the button down and the knife slices their hand off. So they would need to redesign the system to make sure that both of the operator's hands need to press a button at the same time before the knife will actually slice the object. So this is just an example of how important it is to actually think safety in the design of the system during the development of the system. So the case study that we looked at here was an autonomous combined harvester. And if you look on the figure on the right, it's just a 3D image of a combined harvester, and as you can see, it's a bulky system. They can weigh up to 15 tons or maybe even more. Their dimensions are also quite big. For example, it can be 10 meters long or 3 meters wide. So if this system drives over an animal, it will definitely kill it, especially with the knives at the bottom of the system, as of the I don't remember what this is called, but as you can see, the knives here, they will slice the creature, unfortunately. So this is defined as as a safety critical system. So it's important to have a safety case of the system, and if we're looking at an autonomous combined harvester, there's a lot that can go wrong. For example, if we look at the figure on the left, it's just kind of an overview of how a combined harvester may look, and you can see there's a small fawn hiding in between the crops. To give you a better idea, on this picture it's obvious to see the fawn, but in some cases, for example here, it won't be that obvious to see that there's an animal hiding between the crops, especially if you see this from the side and not from a top view, a bird eyes view. So it's important to also use different kinds of sensors in order to gain as much information about the environment surrounding the combined harvester as possible, so that the system can avoid driving over these creatures. The motivation for using co-simulation for this system is that it is expensive to perform physical tests. Every time we talked to, it was in collaboration with a company. We talked to an engineer from a company that was developing this, and they said that when they want to test a combined harvester, you need to find a field to test it on. Usually, if you have something with the images that you have to look at, or the sensor data, then you also need to make sure that the crops are ripe and ready to harvest. You need to get your combined harvester out there to the field. You need to agree with a farmer on using this field. So this is just the few steps that you need to do, and there are much more, I'm sure, that I don't even know about, just to test some specific detail, for example. Another problem is that the environment around a combined harvester is uncontrollable. For example, it can be, maybe you want to test the system in very windy conditions, or in heavy rain, and so on. This is really difficult because you would have to wait for the specific conditions to all be satisfied, or the specific constraints to all be satisfied before you can actually go and physically test your system. Another thing is that these tests may be unethical. If you actually want to test that the system will, for example, avoid a deer hiding or that running in front of the combined harvester, then you can't just go out in the field and test this, and then if it goes wrong, oh well, it died. It's something that you will not physically test in that way, not with living animals. So that's why we can see the potential of using co-simulation in cooperation with, during the development process of this safety critical system. Yes. So the development process, or the methodology that we used, was as you can see here, and throughout the next 15-20 slides, I will explain the different steps in the process, and also give some background information for each concept. But as you can see, we have 6 main stages, I would say, where we have something called a fault tree analysis, some safety goals, and then we determine here, after we have defined the safety goals, if we can obtain evidence using co-simulation or not, and I will also talk more about this later. And then in the end, we can see that the co-simulation results can be used as evidence that prove that these safety goals are fulfilled. Yes. Okay. So the first thing I want to explain is the type of safety case that we safety case process that we have followed. So as I mentioned earlier, there's some systems or some processes where you would develop the system first and then create the safety case and look at the safety aspects of the system. But there is also another process which is called a phased safety case process, where there are three main phases: the preliminary, the interim, and operational. And as you can see on the graph, the preliminary requires not a lot of effort in the start, and the effort increases the longer, the further you are along the process. And in the end, hopefully you have an operational safety case where you will test a lot of your stuff on this physical system. So when we're looking at the preliminary, it's in the start of the system, of the development of the system, where you have defined you want this type of system and some requirements, but not every single requirement is clear. You might not know exactly which components you need, and so on. So it's still in the start of the development process. Yes, the operational safety case is when you actually have defined everything and it is right before you want to deploy the system that you will be working with this safety case. So how I see it with the co-simulation, well, something to note is that we only focus on the preliminary safety case in this paper. But how I see it is that in the preliminary you kind of have a model with a high abstraction level and low fidelity, so it kind of it only focuses on the main aspects that you are that you are trying to prove safe in the system. While in the operational safety case you would actually need to focus on everything, and for example, if you I believe that co-simulation can be used there with, for example, software in the loop. So instead of needing to go and test your software in the physical system, you can try testing it in a co-simulation. Yes, but we focus on the preliminary safety case in this paper, so the abstraction level is really high. Okay, so the first thing that we need to do is provide a system description, which I already gave, and the next thing is to identify which hazards exist. And this was done by reading ISO standards for the safety of agricultural vehicles. They have defined some hazards, and by talking to an agricultural engineer from the company ACCO, and by reading on the internet and trying to find out what can be hazardous for combine harvesters. So the five hazards that we found, there are of course many more, but the five that we found or focused on were collision with object, damage to unharvested crops. That could be if the harvester runs over some crops without harvesting them or something. Fire ignition. Apparently in some countries, if it is the risk of the combine harvester catching fire is quite high, for example in Australia or New Zealand. Damage to harvesting machinery, and that could be fire, but that could also be if there are stones, large stones on the crop field that can damage the knives on the cutter bar, or if they get into the system they may damage other parts of the system. Contamination of harvested crops. This can, for example, be if the harvester has a tank where they harvest, where they contain the harvested crops, and if the harvester, for example, drives over a deer or another animal, then the animal's insides will be added into the tank where the harvested crops are, and therefore you will need to throw these the harvested grain or whatever it is out, and you will need to clean the whole system, and you will need to clean the whole vehicle and the system. So after identifying the hazards, we also looked at what could be the root causes of these hazards. And there are different methods that can be used to determine this. But we chose to use the fault tree analysis because of its simplicity. And actually, typically, you would use combine different methods to detect the root causes of a hazard. And fault tree analysis, as you can see, we have our hazard up here, H1 for example, and we have an OR gate. So this can be caused by either obstacle not detected by sensor, obstacle detection, algorithm failure, and so on. So you have kind of a tree structure where you define it can be because of this or this or this or this, for example. And here we've defined that incorrect setup of machine is, for example, due to this specific root cause. So when you have a circle, it's because of this specific root cause. And only this fault tree will be shown here. The rest of the fault trees can be found in the thesis. After identifying the hazards and their root causes, we perform risk assessment, and that is to determine which hazards make sense to focus on and how much effort should be used on each hazard. Of course, every hazard must be mitigated, or well, its probability of occurring or risk or accident severity should be reduced. But as you can see, we have defined hazard 1 and hazard 3 as their acceptability is intolerable, and therefore we choose in this paper just to focus on these two hazards from now on. And as you can see, ALARP stands for as low as reasonably possible. Okay. Yes. So the next thing I will talk about is, now we have defined the hazards and the root causes. The next thing I will explain is the goal structuring notation, and then I'll show you how we can create safety objectives in a goal structuring notation. So here, the first thing that we have here, G1, is the goal. It's defined as a goal element in the goal structuring notation, and this can be seen as the same as a safety objective in a safety case. So GSN is just a way to visualize how a safety objective is, or how an evidence is related to a safety objective by using a specific argument, for example. And this is the strategy element, which is the same as the argument. So you describe how is kind of your argument used for that this evidence, for example, here it fulfills this safety goal, or that this safety goal is a sub goal of this safety goal. And this is evidence, also called solution in GSN, and an away goal where we can refer to this, where we use the claims made in this away goal to as part of the evidence that we have here. So if we have proved something here, then we can use it in this part, this solution. Yes, so here we kind of explain how we formalize the safety goals using fault tree analysis. And as you can see, the hazard that we have here gives us, allows us to define a safety goal that the system should avoid colliding with obstacles. Our argument is to eliminate all the root causes of the hazard, and this is just a simple fault tree and a simple GSN, so the real ones that we made are much larger, of course. And then, for example, the root cause could be heavy rain or dense fog, and then we will say, okay, our goal is to make sure that the system can tolerate operating in heavy rain. And so that's how we went from fault tree analysis to defining safety goals in the goal structuring notation. Yes, so the next step is to determine where to use cosimulation, if it makes sense for any of the hazards that we have. If we look at the root causes of hazard 1, they're mainly related to software and sensors, and how the environment affects this. So this can be mitigated, these root causes can be mitigated mainly using a combination of software and redundant sensors, for example, or using different sensors and algorithms for this. while H3, which was a fire ignition, the root causes are mainly related to something mechanical, and therefore there isn't a lot of it's not really focused on the integration between software and hardware. It could, for example, be just using isolating material or something else. So therefore we focus on producing evidence for hazard 1 using cosimulation. So the next step is to design the models and scenarios that should be used in a cosimulation. And here we have we focus on 3 root causes of the hazard, which are these 3 hazardous events: dense fog, heavy rain, inaccurate sensor measurements. And we define, for example, the vehicle speed, the initial distance to obstacle, where we test these events. And these scenarios must be defined so that they actually are related to the physical system, but will be performed in a co-simulation. For example, you wouldn't want to test these events with real living creatures, but you could simulate animals or obstacles on the path of the vehicle instead. Yes, so we test with 3 different vehicle speeds, as you can see. So that's kind of just like an overview of the scenarios, and we'll go deeper and determine which parameters to change the further into we get into the process. So the next step is to identify the models, and here we used a controller and a vehicle model for the combined harvester, which are part of some of the examples in the InterCPS toolchain, where the controller is written in Overture and it's a pure pursuit controller, and the vehicle dynamics are simulated in 20sim using a bicycle model. And the rest of the models, so the FMUs from functional mockup units, they are created using PyFMU, which is FMUs created using Python. So what we looked at is how can we model these scenarios of, for example, dense fog and heavy rain. So we read articles of where other researchers have tested LiDARs and cameras in dense fog, different dense fogs, and different heavy rain scenarios, and they have described that the main effect is that the maximum sensor range, viewing range of the sensor is decreased, and this is the same in both dense fog and heavy rain scenarios. So we can, in principle, combine these 2 environmental conditions as into one sensor model where we can adjust it using a parameter. So as you can see here, for example, the true sensor model on the system could be as we have on the left, with a LiDAR and a radar, and while the simulated one can be on the right, while we're still in the preliminary safety case and identifying which sensors would we need to use and so on. So we can still leave that open. So as you can see, we have a minimum and a maximum range for the sensors, and these are just parameters that can be adjusted for the co-simulation, so we can try simulating dense fog or good visibility and so on, and test how the system operates in these different scenarios. So what we do is we have a supervisory controller, and I'll show you a demo in a sec. A supervisory controller that when it detects obstacles within its braking distance, it will perform a safety stop. So let us try running this, and it starts some Python processes for each PyFMU. So this is the good thing about this, is that we could easily, just using Python, QT graph, I think it was called, to visualize how the system is moving, how the vehicle is moving, and if there are obstacles in its path, how it will perform a safety stop. So we can also show to the regulatory bodies, hey, we have a video of this system and you can see that it performed a safety stop here in this specific condition where we model this specific scenario or hazardous event. So this is something I think is really useful using the cosimulation. It's not just a bunch of code only, but you also have a visualization to achieve a better understanding of why do we define the system as safe in this scenario. Yes, so the results that we got were that we could successfully simulate the dense fog and rain scenarios where the system performed a safety stop, but when we simulated inaccurate sensor measurements, the system didn't perform a safety stop, and that just means that we need to go back and make some safety improvements to our safety supervisory controller. Something you have to notice here is also that we haven't validated the models that we used. So we need to ensure that these models that we used sufficiently represent the system in with respect to the different aspects that we have focused on in the model. Yes, so this is the complete process that we used. And so if we briefly look at when does it make sense to use this technique, you have to always think about how much time you will spend creating a model of the system and which type of system it is. For example, I think usually in many cyber-physical systems it would make sense to use co-simulation because you have a collaboration between software and a physical system and a dynamic environment, for example. And especially in the case of the case study, we had, for example, testing in dense fog or heavy rain is difficult, and maybe the regulatory body wouldn't expect you to test it, but just say we did this, this, and this, so we believe that it should be good enough. But by using co-simulation, you can test the system in the controlled environment that you need and prove and show that when we test the system in this case and we have validated the model, that this shows that this system is safe and performs a safety stop in this case. In some cases, it won't make sense to use co-simulation. For example, if you have a lot of system tests performed before and you're just upgrading the version of a system of a vehicle, for example, then maybe it will make sense to just use some mathematical proof and hazard logs from the older version and the system tests and a number of system tests. Yes, so in general what I'm trying to tell you here is that the main steps that we have contributed with are trying to use co-simulation in safety case with steps 3, 4, and 5. So something that we also need to consider when looking into co-simulation and how we can use it in safety cases or in the development of safety critical systems is that right now there are still some practical limitations. For example, it will hopefully in the future the tools will be much more mature. For example, we had some problems with exporting 20 FMUs comparing it to the traditional creation techniques. So the conclusion is that co-simulation may make sense to use when working with systems where there is complex software and hardware interactions, and especially I would say in cases where you cannot physically test the system in a, for example, controlled environment. And something, the advantage, other advantage of using co-simulation also allows us to visualize our results and allow the regulatory body to better understand why the system is safe, should be safe. Future work is of course to use co-simulation in the interim and operational safety case of the system, and I think especially looking at the operational safety case and using software in the loop could be interesting to look at. And determining the amount of parameters per scenario. For example, I only took the worst case values to determine if for example, dense fog and heavy rain, if the system was safe in these scenarios, but there should be maybe some guidelines trying to understand when have we chosen enough parameters to simulate per scenario. of course, validating the model is part of the future work, and something interesting could be to evaluate it on other systems, for example, medical devices, where you have humans operating the system also. Yes. Yeah, and our acknowledgements are just thank you to Martin from ACCO, and thank you to the anonymous reviewers of the paper.